Ammonium chloride corrosion as a part of uniform or localized loss in thickness phenomena. Description of ammonium chloride corrosion based on API 571, general or localized corrosion, often pitting, normally occurring under ammonium chloride or amine salt deposits, often in the absence of a free water phase. Ammonium chloride corrosion refers to the chemical process where materials, typically metals, undergo deterioration due to the presence of ammonium chloride or NH4Cl. This type of corrosion can manifest as either general, uniform, corrosion or localized corrosion, each with distinct mechanisms and characteristics. The first is general or uniform corrosion. In the case of general corrosion, ammonium chloride interacts uniformly across the entire exposed surface of the metal. When metals such as steel, copper, or aluminum are exposed to ammonium chloride in the presence of moisture or water, a series of chemical reactions occur. Ammonium chloride dissociates into ammonium and chloride ions. The chloride ions penetrate the metal surface, disrupting the passive oxide layer that normally protects metals like aluminum and steel. The chloride ions, combined with moisture, facilitate the formation of soluble metal chloride complexes, which dissolve into the surrounding environment. This process results in a uniform thinning of the metal surface over time, leading to loss of structural integrity. Localized corrosion. Localized corrosion caused by ammonium chloride is more aggressive and occurs in specific areas, leading to pitting, crevice corrosion, or filiform corrosion. The mechanisms include pitting corrosion. Chloride ions concentrate at specific sites, such as scratches, inclusions, or irregularities on the metal surface, leading to the breakdown of the passive film locally. Crevice corrosion occurs in confined spaces, for example under deposits, gaskets, or crevices, where the local environment becomes more aggressive due to differential aeration and accumulation of ammonium chloride. Filiform corrosion, characterized by thread-like corrosion fronts under coatings, often initiated in moist environments with ammonium chloride vapors or solutions. Chemical reactions and impact. The presence of ammonium chloride accelerates corrosion through several pathways: formation of metal chlorides, which are often soluble and lead to metal loss. The acidic environment created by ammonium ions reacting with moisture can lower pH locally, further destabilizing passive films. The chloride ions are particularly aggressive in breaking down protective oxide layers, especially in stainless steels and aluminum alloys. Factors influencing ammonium chloride corrosion includes: the first is moisture levels. High humidity or water presence enhances corrosion. The second is temperature. Elevated temperatures increase reaction rates and chloride mobility. The third is metal composition. Different alloys have varying resistance. Stainless steels are more resistant but can still be affected. The fourth is environmental conditions. Presence of other chemicals, pollutants, or salts can exacerbate corrosion. Practical implications. Ammonium chloride-induced corrosion is a concern in industries such as battery manufacturing and storage, where ammonium chloride is used in electrolytes; textile and dye industries, where ammonium chloride is involved in processing; electronics and electrical systems, where exposure to ammonium chloride vapors can lead to corrosion of conductive parts; heating and cooling systems, where deposits containing ammonium chloride can cause localized damage. In conclusion, ammonium chloride corrosion involves complex electrochemical and chemical processes that can lead to both uniform thinning and localized damage of metal surfaces. The chloride ions play a critical role in disrupting protective oxide layers, accelerating metal dissolution, and causing structural failures. Proper material selection, environmental control, and protective coatings are essential to mitigate this type of corrosion. Ammonium chloride corrosion affected materials based on API 571. All commonly used materials are susceptible, in order of increasing resistance: carbon steel, low alloy steels, 300 series SS, alloys 400, duplex SS, 800, and 825, alloys 625 and C276, and titanium. The materials affected by ammonium chloride corrosion, whether it manifests as general, uniform, or localized corrosion, primarily include various metals and alloys that are commonly used in industrial, structural, and electrical applications. The susceptibility of these materials depends on their chemical composition, surface properties, and environmental conditions. Common materials affected by ammonium chloride corrosion includes, number 1 is, carbon steel and low alloy steels, the vulnerability of the carbon steel and low alloy steels. Carbon steels are susceptible to ammonium chloride corrosion because their passive oxide layers can be disrupted by chloride ions. Corrosion characteristics commonly affected to the carbon steel and low alloy steels, both uniform thinning and localized pitting can occur. The chloride ions penetrate any surface imperfections or existing defects, initiating localized corrosion. The impact of ammonium chloride corrosion to this carbon steel and low alloy steels is, this leads to reduced mechanical strength and potential structural failure over time. The number 2 of the common materials affected by ammonium chloride corrosion is, stainless steels, such as types 304, 316, the vulnerability of stainless steels. Although stainless steels are generally resistant due to their chromium oxide passive layer, chloride ions can compromise this protective film. The corrosion characteristics occurs on stainless steels are, localized pitting and crevice corrosion are common, especially in environments with high chloride concentrations. Pitting initiates at weak points, such as welds, scratches, or surface inclusions. The impact of stainless steels to ammonium chloride corrosion, pitting can lead to rapid failure if not detected early, particularly in chloride-rich environments. The number 3 of the common materials affected by ammonium chloride corrosion is, aluminum and aluminum alloys, the vulnerability of aluminum and aluminum alloys. Aluminum naturally forms a protective oxide film, but chloride ions can penetrate this layer, causing localized corrosion. The corrosion characteristics occurs on aluminum and aluminum alloys, pitting corrosion is prevalent. Crevice corrosion may develop in confined spaces. The impact of aluminum and aluminum alloys to ammonium chloride corrosion, structural weakening and surface damage, especially in marine or humid environments. The number 4 of the common materials affected by ammonium chloride corrosion is, copper and copper alloys, such as brass, bronze, the vulnerability of copper and copper alloys. Copper forms protective patinas, but chloride ions can convert these into soluble copper chloride complexes. The corrosion characteristics occurs on copper and copper alloys, general corrosion is less common than localized pitting. When affected, pitting is the predominant form, leading to holes and structural compromise. The impact of copper and copper alloys to ammonium chloride corrosion, damage to electrical components, plumbing, and decorative elements. The number 5 of the common materials affected by ammonium chloride corrosion is, nickel and nickel alloys, the vulnerability of nickel and nickel alloys. Generally more resistant but can still be affected under specific conditions, particularly in highly concentrated chloride environments. The corrosion characteristics occurs on nickel and nickel alloys. Localized pitting and crevice corrosion can occur, especially in less resistant alloys. The impact of nickel and nickel alloys to ammonium chloride corrosion, potential failure of critical components in chemical processing or marine environments. The number 6 of the common materials affected by ammonium chloride corrosion is, titanium and tantalum, the vulnerability of titanium and tantalum. These are highly resistant to chloride-induced corrosion due to their stable oxide layers. The corrosion characteristics occurs on titanium and tantalum, minimal to no effect under normal conditions, though extreme environments might cause localized attack. The impact of titanium and tantalum to ammonium chloride corrosion, usually unaffected, suitable for highly aggressive environments. The number 7 of the common materials affected by ammonium chloride corrosion is, other materials, such as zinc, lead, tin, the vulnerability of zinc, lead, and tin. These metals are generally less resistant and can undergo uniform or localized corrosion. The corrosion characteristics occurs on zinc, lead, and tin. Zinc, for example, may corrode uniformly, while lead and tin may experience localized attack. The impact of zinc, lead, and tin to ammonium chloride corrosion, material degradation and potential failure in specific applications. In summary, most susceptible materials, carbon steels, low alloy steels, aluminum alloys, copper alloys, and certain zinc-based materials, moderately resistant, nickel alloys, stainless steels, depending on grade and environment, highly resistant, titanium, tantalum, and other noble metals. In practical consideration, Materials exposed to ammonium chloride should be selected based on their corrosion resistance, especially in humid or chloride-rich environments. Protective coatings, corrosion inhibitors, and environmental controls are also essential to mitigate damage. Ammonium chloride corrosion critical factors based on API 571, number A, concentration, NH3, HCl, H20 or amine salts, temperature and water availability are the critical factors. Number B, ammonium chloride salts may precipitate from high-temperature streams as they are cooled, depending upon the concentration of NH3 and HCl, and may corrode piping and equipment at temperatures well above the water dew point, greater than 300 degrees Fahrenheit or 149 degrees Celsius. Number C, ammonium chloride salts are hygroscopic and readily absorb water. A small amount of water can lead to very aggressive corrosion, greater than 100 mm per year or greater than 2.5 mm per year. Number D, ammonium chloride and amine hydrochloride salts are highly water-soluble, highly corrosive and form an acidic solution when mixed with water. Some neutralizing amines react with chlorides to form amine hydrochlorides that can act in a similar fashion. Number E, corrosion rates increase with increasing temperature. Number F, when they deposit above the water dew point, a water wash injection may be required to dissolve the salts. The critical factors influencing ammonium chloride corrosion, whether it manifests as general, uniform, or localized corrosion, are various environmental, material, and operational parameters that determine the rate, severity, and type of corrosion experienced by susceptible materials. Understanding these factors is essential for predicting, preventing, or mitigating damage caused by ammonium chloride. Critical factors influencing ammonium chloride corrosion includes, number 1 is chloride ion concentration. Description: the amount of chloride ions present in the environment directly impacts corrosion severity. Impact: higher chloride concentrations increase the aggressiveness, promoting pitting, crevice, and other localized corrosion forms. Elevated chloride levels disrupt passive films more effectively, leading to faster metal dissolution. Threshold: even low levels can cause corrosion in susceptible materials. However, as concentration increases, the corrosion rate accelerates significantly. Number 2 is moisture and water presence. Description: moisture acts as a medium for electrolyte formation, enabling ion mobility and electrochemical reactions. Impact: moist environments facilitate the dissociation of ammonium chloride into ammonium and chloride ions, which are critical for corrosion processes. Water availability influences localized corrosion, such as crevice and pitting, especially in confined spaces where water can stagnate. Number 2 is moisture and water presence. Description: moisture acts as a medium for electrolyte formation, enabling ion mobility and electrochemical reactions. Impact: moist environments facilitate the dissociation of ammonium chloride into ammonium and chloride ions, which are critical for corrosion processes. Water availability influences localized corrosion, such as crevice and pitting, especially in confined spaces where water can stagnate. Number 3 is temperature. Description: elevated temperatures enhance chemical reaction rates and chloride ion mobility. Impact: higher temperatures accelerate corrosion processes, increase the rate of metal dissolution, and can destabilize protective oxide films. This effect is especially pronounced in localized corrosion, where aggressive conditions develop rapidly. Number 4 is environmental pH. Description: the acidity or alkalinity of the environment influences corrosion behavior. Impact: acidic conditions, low pH, exacerbate corrosion by destabilizing passive films. Ammonium ions can generate localized acidity when reacting with moisture, promoting further corrosion. Number 5 is material composition and surface condition. Description: the chemical makeup, microstructure, and surface finish of materials influence their corrosion susceptibility. Impact: materials with passive oxide layers, e.g., stainless steel, aluminum, are more resistant but can still suffer localized attack if the layer is compromised. Surface defects, scratches, and inclusions act as initiation sites for localized corrosion. Number 6 is presence of other chemicals or contaminants. Description: additional chemicals such as sulfates, nitrates, or pollutants can interact synergistically with ammonium chloride. Impact: these contaminants can alter the electrochemical environment, increase acidity, or catalyze corrosion reactions. Number 7 is design and geometry of the material or structure. Description: the physical configuration influences fluid flow, crevice formation, and drainage. Impact: crevices, pits, or confined spaces trap moisture and chloride ions, fostering localized corrosion. Poor drainage or design flaws can lead to stagnant areas where chloride concentration and moisture accumulate. Number 8 is protective coatings and surface treatments. Description: coatings, paints, or surface treatments can inhibit chloride ingress. Impact: degradation or damage to coatings exposes underlying metal, increasing susceptibility. The integrity and adhesion of protective layers are critical to preventing chloride penetration. Number 9 is time of exposure. Description: duration of exposure to ammonium chloride environments influences the extent of corrosion. Impact: longer exposure allows for more extensive material degradation, especially if critical factors like moisture and chloride concentration are sustained. The severity and type of ammonium chloride corrosion are governed by a complex interplay of these factors. Controlling and optimizing these parameters through material selection, environmental control, and design improvements are essential steps to mitigate corrosion risks. Ammonium chloride corrosion affected units or equipment based on API 571. Number A, crude tower overheads. Number 1, tower top trays, overhead piping and exchangers may be subject to fouling and corrosion. Deposits may occur in low flow zones due to ammonia and/or amine chloride salts condensing from the vapor phase. Number 2, top pump-around streams may be affected if ammonia or amine chloride salts are present. Number B, hydroprocessing. Reactor effluent streams are subject to ammonium chloride salt fouling and corrosion. Water washing may be required if exchanger fouling or loss in duty occurs. Number C, catalytic reforming. Reactor effluent streams and the H2 recycle system are subject to ammonium chloride salting and corrosion. Number D, FCCU and coker fractionator overheads and top pump-arounds are subject to ammonium chloride corrosion and salting. The units or equipment affected by ammonium chloride corrosion, whether it manifests as general, uniform, or localized corrosion, span a wide range of industrial, structural, and electrical systems. The susceptibility of these units depends on their material composition, operational environment, design, and exposure duration. Affected units and equipment by ammonium chloride corrosion includes: number 1 is heat exchangers. Description: devices used in chemical processing, power plants, and HVAC systems to transfer heat between fluids. The vulnerability of ammonium chloride corrosion to heat exchangers includes: heat exchanger tubes and shells made of metals like carbon steel, stainless steel, or aluminum are prone to chloride-induced corrosion. Localized pitting can compromise heat transfer efficiency and cause leaks. The impact of ammonium chloride corrosion to heat exchangers: reduced operational lifespan, potential leaks, and catastrophic failure if corrosion penetrates deeply. Number 2 is piping systems. Description: networks of pipes transporting fluids in chemical plants, refineries, marine vessels, and cooling systems. The vulnerability of ammonium chloride corrosion to piping systems includes: susceptible at welds, joints, bends, and areas of stagnation. Chloride ions can cause uniform thinning or localized pitting, especially in crevices or stagnant zones. The impact of ammonium chloride corrosion to piping systems: leaks, ruptures, and operational shutdowns, increased maintenance costs. Number 3 is reactors and vessels. Description: containers used for chemical reactions, storage, or processing. The vulnerability of ammonium chloride corrosion to reactors and vessels includes: inner surfaces and weld zones are vulnerable. Corrosion can lead to thinning, cracking, or perforation. The impact of ammonium chloride corrosion to reactors and vessels: safety hazards, contamination, or loss of containment. Number 4 is cooling towers and condensers. Description: structures involved in heat rejection and cooling processes. The vulnerability of ammonium chloride corrosion to cooling towers and condensers includes: aluminum or steel components exposed to chloride-rich water are at risk. Localized corrosion can occur at water stagnation zones or where biofouling occurs. The impact of ammonium chloride corrosion to cooling towers and condensers: reduced efficiency, structural integrity issues. Number 5 is electrical and instrumentation components. Description: electrical enclosures, control panels, and wiring often use metals susceptible to chloride attack. The vulnerability of ammonium chloride corrosion to electrical and instrumentation components includes corrosion of electrical contacts and enclosures can cause failures. The impact of ammonium chloride corrosion to electrical and instrumentation components, malfunction of control systems, safety risks. Number 6 is marine and ship equipment. Description: ship hulls, propellers, ballast tanks, and other submerged structures. The vulnerability of ammonium chloride corrosion to marine and ship equipment includes constant exposure to chloride-rich seawater accelerates both general and localized corrosion. Pitting and crevice corrosion are common in ship hulls and propellers. The impact of ammonium chloride corrosion to marine and ship equipment, structural degradation, increased. Maintenance, potential safety hazards. Number 7 is structural components. Description: supports, frameworks, and foundations made of metals. The vulnerability of ammonium chloride corrosion to structural components includes structural steel components can experience uniform thinning or localized pitting, critical in environments with high chloride exposure, such as coastal or industrial zones. The impact of ammonium chloride corrosion to structural components, compromise structural integrity, safety risks. Number 8 is storage tanks and containers. Description: tanks for chemicals, fuels, or water, often made of steel, stainless steel, or aluminum. The vulnerability of ammonium chloride corrosion to structural components includes corrosion at welds, seams, or areas with surface defects. Localized pitting can lead to leaks or ruptures. The impact of ammonium chloride corrosion to structural components. Environmental contamination, safety hazards. Number 9 is valves, fittings, and flanges. Description: key components in piping and process systems. The vulnerability of ammonium chloride corrosion to valves, fittings, and flanges includes regions of crevices and joints are prone to crevice corrosion. The impact of ammonium chloride corrosion to valves, fittings, and flanges, leaks, operational failures. Number 10 is heat treatment equipment and furnaces. Description: equipment used in metallurgical processes. The vulnerability of ammonium chloride corrosion to heat treatment equipment and furnaces includes exposure to chloride vapors or residues can cause corrosion of interior surfaces. The impact of ammonium chloride corrosion to heat treatment equipment and furnaces, equipment degradation, safety concerns. The susceptibility of equipment to ammonium chloride corrosion underscores the importance of material selection, protective coatings, and environmental controls. Regular inspection and maintenance are critical in high-risk environments to detect early signs of corrosion, especially localized forms like pitting and crevice corrosion. Ammonium chloride corrosion appearance or morphology of damage based on API 571. Number A, the salts have a whitish, greenish, or brownish appearance. Water washing and/or steam out will remove deposits so that evidence of fouling may not be evident during an internal visual inspection. Number B, corrosion underneath the salts is typically very localized and results in pitting. Number C, corrosion rates can be extremely high. The appearance or morphology of ammonium chloride corrosion, whether it manifests as general, uniform, or localized corrosion, provides critical insights into the nature, severity, and underlying mechanisms of the damage. Understanding these morphological features is essential for diagnosing corrosion types, assessing material integrity, and implementing appropriate mitigation strategies. Appearance and morphology of ammonium chloride corrosion includes: number 1 is general or uniform corrosion morphology. The appearance of general or uniform corrosion includes surface wasting. The most characteristic feature of general corrosion is a relatively uniform and widespread material loss across the exposed surface. Surface roughness: the surface becomes rough, dull, and often exhibits a matte appearance due to metal dissolution, color changes, the formation of corrosion. Products such as ammonium chloride residues may impart a white or powdery deposit on the surface. The morphological features of general or uniform corrosion includes thinning of material. The metal surface gradually thins in a relatively even manner, with no pronounced localized features. Corrosion layers: formation of corrosion films or layers composed of metal chlorides or oxides, which may be loosely adherent or compact depending on environmental conditions. Surface texture often appears as matte or dull, with a uniform matte gray or white coating if corrosion products are present. The process indicators of general or uniform corrosion includes, the corrosion process is driven primarily by the uniform attack of chloride ions, moisture, and temperature, leading to even dissolution. The appearance and morphology of ammonium chloride corrosion. Number 2 is localized corrosion morphology, pitting, crevice, and spotting. The appearance. Localized corrosion exhibits distinct, often sharply defined features that differ markedly from uniform corrosion. The key forms include, number A, pitting corrosion, small cavities or pits, deep, narrow, and well-defined cavities or holes on the surface. Size distribution, pits can vary from microscopic to several millimeters in diameter, often dispersed randomly. Surface roughness, pitted areas display a rough, uneven surface with sharp edges around the pits. Corrosion products, often surrounded by dark or colorless deposits, sometimes accompanied by white ammonium chloride residues. Crevice corrosion. Appearance of local corrosion morphology, localized attack in gaps, occurs within crevices, joints, or under deposits. Morphology, features include darkened, roughened, and often undercut regions where the metal has been selectively attacked. Appearance, the crevice areas can appear as narrow lines, cracks, or undercut zones with significant metal loss. Spotting or spot corrosion. Appearance of local corrosion morphology, small, discrete spots, usually less aggressive than pitting but indicative of localized attack. Appearance, small, often circular, or irregular spots that may be darker or lighter than the surrounding surface. The morphological features of localized corrosion includes, deep penetrations, pits often extend below the surface, creating a cavity. Rough edges, edges around pits or crevices are sharp and undercut. Corrosion products, accumulation of white ammonium chloride crystals or other corrosion products within pits. Surface discoloration, localized discoloration or staining often accompanies pits or crevices. The appearance and morphology of ammonium chloride corrosion. Number 3 is corrosion products and deposits, includes, white or powdery residues. Ammonium chloride deposits appear as white, crystalline, or powdery deposits on or around corroded areas. Crystalline structures, crystals may form within pits or crevices, often with a characteristic flaky or granular appearance. Coloration, areas of corrosion may be accompanied by rust-colored, iron oxides, greenish, copper salts, or other colored deposits depending on the metal involved. Visual indicators of severity, early stage, surface appears slightly roughened with minor discoloration. Deposits may be faint. Moderate stage, visible pits, crevice damage, or localized discoloration. Deposits more prominent. Severe stage, deep pits, perforations, or cracks. Extensive deposits of corrosion products. Possible structural compromise. In summary, general corrosion manifests as a uniform dulling, roughening, or thinning of the surface, often accompanied by a white or powdery deposit. Localized corrosion such as pitting and crevice attack presents as sharp, deep cavities or undercut regions, with characteristic pits, rough edges, and often crystalline ammonium chloride deposits. Understanding these morphological features aids in diagnosis, evaluation of damage severity, and planning for repair or mitigation measures. Ammonium chloride corrosion prevention and mitigation. Based on API 571, alloys that are more pitting resistant will have improved resistance to ammonium chloride salts, but even the most corrosion resistant nickel-base alloys and titanium alloys may suffer pitting corrosion. Number A, crude unit. Number 1. Limit salts by limiting chlorides in the tower feed through desalting and/or the addition of caustic to the desalted crude. Number 2. A water wash may be required in the crude tower overhead line to flush the salt deposits. Number 3. Filming amine inhibitors are often added to control corrosion. Number B. Hydroprocessing. Number 1. Limit chlorides in the hydrocarbon feed to the reactor. Number 2. Limit chlorides in the makeup hydrogen supply. Number 3. A continuous or intermittent water wash may be required in the reactor effluent to flush out the salt deposits. Number C. Catalytic reforming. Number 1. Reactor effluent can be treated to remove the chlorides. Number 2, water washing has been used in some cases but the system must be carefully designed. Number 3, some tower overheads may require neutralizing or filming amines. Prevention and mitigation of ammonium chloride corrosion, whether it manifests as general, uniform, or localized corrosion, are critical for maintaining the integrity, safety, and longevity of equipment and structures exposed to chloride-rich environments. A comprehensive approach involves material selection, environmental controls, protective coatings, design considerations, and active maintenance strategies. Below is a detailed explanation of effective prevention and mitigation methods. Prevention and mitigation of ammonium chloride corrosion includes, number 1 is material selection, includes, number A, use corrosion-resistant alloys or high-performance materials, includes, stainless steels, alloys such as 316L, 317L, or higher grades that contain molybdenum or other corrosion-resistant elements, nickel-based alloys, such as Inconel or Monel, which offer superior resistance to chloride-induced corrosion, nonmetallic materials, plastics, PVC, PTFE, composites, or ceramics in environments with high chloride exposure. Material selection. Number B is, material coatings and linings, includes, protective coatings, epoxy, rubber linings, or polyurethane coatings to act as a barrier, galvanization, applying zinc coatings on steel components to provide sacrificial protection. Material selection. Number C to be considered is, material condition, use materials with smooth surfaces, minimal weld defects, and proper heat treatments to reduce susceptibility. Prevention and mitigation of ammonium chloride corrosion. Number 2 is environmental control, includes, number A, control of chloride concentration by, reduce exposure to chloride sources, such as seawater, salt sprays, or chloride-rich chemicals, use deionized or treated water in cooling systems to minimize chloride content. Environmental control. Number B is, control of humidity and temperature by, maintain low humidity levels to inhibit moisture-driven corrosion, avoid high-temperature environments that accelerate corrosion processes. Environmental control. Number C is, corrosion inhibitors by, add corrosion inhibitors compatible with the process that can form protective films on metal surfaces. Examples include ammonium salts or organic inhibitors designed for chloride environments. Environmental control. Number D is, proper drainage and ventilation, ensure that condensate, stagnant water, or deposits do not accumulate, especially in crevices or under insulation. Prevention and mitigation of ammonium chloride corrosion. Number 3 is design considerations, includes, number A, avoid crevices and stagnant zones by, design equipment with smooth internal surfaces, rounded joints, and minimal crevices, implement proper drainage to prevent water or chloride accumulation. Design considerations. Number B is, use of protective barriers. Incorporate physical barriers such as coatings, wraps, or sacrificial layers. Design considerations. Number C is, regular inspection points, designed for easy access to monitor critical areas prone to corrosion. Prevention and mitigation of ammonium chloride corrosion. Number 4 is protective coatings and surface treatments. Number A is, coatings, apply corrosion-resistant paints, epoxies, or fluoropolymer coatings. Use specialized chlorides-resistant coatings in high-risk areas. Protective coatings and surface treatments. Number B is, surface treatments, passivation of stainless steels to enhance resistance. Application of inhibitors or sealants within crevices or weld zones. Prevention and mitigation of ammonium chloride corrosion. Number 5 is operational and maintenance strategies. Number A is, regular inspection and monitoring, conduct visual inspections for early signs of corrosion, pitting, deposits. Use non-destructive testing, NDT, methods such as ultrasonic or radiography. Operational and maintenance strategies. Number B is, cleaning and removal of deposits, periodic cleaning to remove ammonium chloride residues and prevent localized attack. Use of appropriate cleaning agents that do not damage protective coatings. Operational and maintenance strategies. Number C is, cathodic protection, applying sacrificial anodes or impressed current systems to prevent metal dissolution. Operational and maintenance strategies. Number C is, repair and replacement, prompt repair of damaged coatings or materials, replace severely corroded components before failure occurs. Prevention and mitigation of ammonium chloride corrosion. Number 6 is chemical treatments and inhibitors, includes, number A, use of corrosion inhibitors specifically formulated for chloride environments, number B, application of passivation treatments or coatings that form insoluble films on metal surfaces, number C, neutralization of ammonium chloride deposits or preventing their formation. Prevention and mitigation of ammonium chloride corrosion. Number 7 is environmental and process controls. Number A, adjust process parameters such as pH, temperature, or chemical composition to reduce chloride activity. Number B, control humidity and moisture levels, especially in enclosed or insulated spaces. Preventing ammonium chloride corrosion is a multifaceted process that combines proper material choices, environmental management, design optimization, protective treatments, and vigilant maintenance. Tailoring these strategies to specific operational conditions and equipment types enhances effectiveness, reduces downtime, and extends the service life of affected units. Ammonium chloride corrosion inspection and monitoring based on API 571. Number A, accumulation of ammonium chloride salts can be very localized and the resulting corrosion may be difficult to detect. Number B, RT or UT thickness monitoring can be used to determine remaining wall thickness. Number C, monitoring of the feed streams and effluent waters will give an indication of the amount of ammonia and chlorides present, however process simulation may be required to determine the concentration and dew point temperatures. If the ammonium chloride salt deposition temperature has been calculated, temperature monitoring and control may be effective for maintaining metal temperatures above the salt deposition temperature. Number D, the presence of deposits is often detected when the pressure drop increases or the thermal performance of exchangers has deteriorated. Number E, corrosion probes or coupons can be useful, but the salt must deposit on the corrosion probe element to detect the corrosion. Inspection and monitoring are critical for early detection, assessment, and management of ammonium bisulfide, NH4HS, corrosion in alkaline sour water environments. Different methods are employed depending on whether the corrosion is general, uniform, or localized, pitting, crevice. Below is a detailed explanation of the most effective inspection and monitoring techniques. Inspection and monitoring methods for detecting ammonium chloride corrosion. Number 1 is visual inspection. This is purposed to identify surface signs of corrosion such as discoloration, deposits, cracks, pits, or erosion. The method of visual inspection are including, use borescopes, fiber optic cameras, or magnifying glasses for internal and inaccessible areas, examine surface roughness, blistering, or flaking. The method details of visual inspection are including, regular surface checks, use magnifying glasses or borescopes for detailed surface examination, detection of deposits, look for white crystalline ammonium chloride residues, which often indicate active corrosion zones, pitting and crevice signs, identify pits or crevice areas with abnormal roughness or discoloration, surface condition documentation, record findings with photographs, measurements, and descriptions for trend analysis. The limitations of visual inspection are including, it cannot quantify corrosion severity, it may miss subsurface or internal corrosion. Inspection and monitoring methods for detecting ammonium chloride corrosion. Number 2 is non-destructive testing or NDT, includes, number A, ultrasonic thickness measurement or UT. The principle of ultrasonic thickness measurement is, it uses high-frequency sound waves to measure the thickness of metal components. The application of ultrasonic thickness measurement is to detect uniform thinning indicating general corrosion, to measures depth of pits or localized thinning, and regular surveys provide data on corrosion rates over time. Inspection and monitoring methods for detecting ammonium chloride corrosion. Number 2 is non-destructive testing or NDT, includes, number A, ultrasonic thickness measurement or UT. The details of ultrasonic thickness measurement is, it requires calibration with known standards, it can do multiple measurements across the surface help identify localized attack. Non-destructive testing or NDT method. Number B is radiographic testing, X-ray or gamma ray. The principle of radiographic testing is, it uses radiation to produce images of internal structures. The application of radiographic testing is to detect internal corrosion, voids, or cracks. Radiographic testing useful for inspecting welds and hidden areas prone to ammonium chloride deposits. The limitations of radiographic testing is, it requires specialized equipment and safety precautions. Non-destructive testing or NDT method. Number C is magnetic particle testing or MT. The application of magnetic particle testing or MT is to detect surface and near-surface discontinuities in ferromagnetic materials, such as cracks or pits. The limitations of magnetic particle testing or MT is not suitable for non-magnetic materials. Inspection and monitoring methods for detecting ammonium chloride corrosion. Number 3 is electrochemical techniques, includes, Number A, potential measurements or half-cell potential monitoring. The purpose of potential measurements is to identify areas at risk of corrosion based on electrochemical potential differences. The application of potential measurements is, it use reference electrodes to measure potential variations across surfaces. It is more negative potentials often indicate active corrosion zones. Electrochemical techniques. Number B is electrochemical impedance spectroscopy. The purpose of electrochemical impedance spectroscopy is to assess the integrity of protective coatings and corrosion activity. The application of electrochemical impedance spectroscopy is, it measures impedance to determine coating degradation or initiation of localized corrosion. Electrochemical techniques. Number B is linear polarization resistance or LPR. The application of linear polarization resistance is to estimate corrosion rates by measuring polarization resistance. High corrosion rates correlate with active corrosion zones. Inspection and monitoring methods for detecting ammonium chloride corrosion. Number 4 is deposit and residue analysis. The purpose of deposit and residue analysis is to confirm the presence of ammonium chloride deposits indicative of corrosion activity. The methods of deposit and residue analysis are included, visual and microscopic examination, for crystalline deposits, chemical analysis, using techniques like X-ray diffraction, XRD, to identify chloride compounds, surface swabs. Laboratory testing, for detailed chemical composition. Inspection and monitoring methods for detecting ammonium chloride corrosion. Number 5 is environmental and chemical monitoring, includes, Number A, moisture and humidity sensors, measure ambient conditions favoring corrosion. Number B, chloride ion concentration testing, use water or deposit samples to quantify chloride levels, correlating with corrosion risk. Number C, pH and temperature monitoring, track environmental parameters influencing ammonium chloride stability and corrosion propensity. Inspection and monitoring methods for detecting ammonium chloride corrosion. Number 6 is advanced and specialized techniques, includes, Number A, fiber optic sensors. Embedded sensors for real-time monitoring of corrosive environments. Number B, acoustic emission or AE monitoring. It detects sound waves generated by crack formation or growth. Number C, electrochemical noise analysis. Monitors spontaneous fluctuations in potential and current to identify localized corrosion activity. Inspection and monitoring methods for detecting ammonium chloride corrosion. Number 7 is corrosion coupons and probes. The purpose of corrosion coupons and probes is to provide a controlled surface for ongoing corrosion rate measurement. The details of corrosion coupons and probes are included, expose metal samples, coupons, in service environments, periodically remove for weight loss measurement or surface analysis. Use multi-electrode probes for localized electrochemical data. Inspection and monitoring methods for detecting ammonium chloride corrosion. Number 8 is data analysis and trend monitoring. Collect data over time to identify increasing corrosion rates. Use software tools for trend analysis and predictive maintenance planning. Inspection and monitoring methods. Final remarks. Effective detection of ammonium chloride corrosion involves combining multiple methods as the following: regular visual inspections for surface signs, electrochemical and ultrasonic testing for quantitative data, chemical analysis to confirm chloride deposits, environmental monitoring to identify corrosive conditions. Implementing a systematic inspection regime with scheduled assessments and real-time monitoring enhances early detection, enabling timely intervention and reducing the risk of severe damage or failure. Thank you.